All right, we're gonna be going over combined loading problem. I've drawn it out here at the very top in this little bubble. We're gonna be focusing on these elements E and F. So as we can see, there's a force F, causing a stress and a lot upon the entire system, and then we also have P causing some reactions upon the system. So if we zoom in right here and look at element A, which is just the beginning part right here, we see that in the y direction there's a shear. There's shear force, and then in the y direction there's also a moment. We also have on the x direction a normal and a moment, and in the z direction a shear and a moment. If we zoom in right here to this part of the component, we have the force coming down, torsional force, a bending force in the y, a bending in the x, an axial force. So really what this is saying is that P right here, this P that is it's causing an axial loading along the x and a bending about the y, and the F right here, this force causes a transverse shear along the y, bending about the x in the clockwise direction, bending about the z in a clockwise direction, as well as torsion about the x axis. So if we zoom into these stress elements right here, this is a stress element E I've drawn right here. So for stress element E, we have a torsional force in the xz direction, and we also have an axial and a bending force. Now for F, which is this guy right here, we have a torsional and a transverse shear, which is going this direction, and then we also have an axial and bending force. So now we're going to start looking at the stress components of E. So in the stress components of E, we have a torsional, a bending. We're just going to go over them real quick. So right here, here's our torsional force. Solving for J equals pi r to the 4th over 2, which in our case gives us 0.31. And then the R, which is given in the problem, is going to be 0.375, and then the force that we solved for is going to be 1200. So in all, that's going to give us an answer of 14,516.16. And then we also have a bending force right here. So that's going to be MC, which the equation is MC over I. I is equal to pi r to the 4th over 4. And this is going to be giving, and the moment is going to be 300 times 4. So what this is going to be giving us is this bending force, which is going to be equal to 490.9 pounds per inch squared. And then lastly, we have an axial load, which is going to be P over A. And A is equal to pi r squared, and in our case that gives us 0.442, and then that gives us, plugging that back into here, we have our axial load equal to 452.49. And now we look at element F and the stress components on it. So we have a transverse, torsional, bending, and another axial. So for the transverse, the equation we're going to be using is 4 over 3 times V over A, V being 300A, as we just solved, is 0.442. So this would give us a transverse of 904.98. And for the torsional, we're going to use the same torsional that we did here. So that was 14,516.16. And then we also have another bending for element F. We're going to do MC over I. So that's going to be 4 times 200 times 375 over 0.11, which is going to give us the answer of 2727.27. And then we also have an axial load, which is going to be P over A, which is going to be 452.49 pounds per inch squared. And now we're going to be going over the Mohr circle for element E.
So after calculating all those stresses, it's easy to now use those stresses that we calculated to find out our principal stresses using Moore's circle. And to draw Moore's circle, we first need the radius of the circle and the center of the circle. And so this is the equation for the radius, and we would plug in our sigma x and our sigma z, which is 0 in this case, and our torsional shear, which is actually our torsional minus our transverse. So that's what's included up here. And then we also need to calculate our principal stresses, and that helps to align the circle a little bit better. And so these are the coordinates: 0, 14,516, and 4,096, 14,516. For these points along this line right here. And so now I'm gonna do element F, which is really just the same thing but with different numbers. So, and it will be in a different plane as well. So this would change from the XZ plane to the XY. And the numbers will be slightly different. So our center for element F was found out to be 3,635, and then you would plug that in here, square it, and then add the shear. And so for element F, again, we have to calculate all the same things, and now we have to focus on the now we have to focus on the XY plane instead of the XZ plane. And so we have different stresses along this plane as opposed to the E plane. In the F plane, we have a transverse shear, which we didn't in the E element. And so we take that into account when calculating our shear, and that's why it's a little lower. And so we also have stress in the Y, and our stress in the X is the same. So we use all that to calculate the radius for Moore's circle, and then the principal stresses. And this is the Moore's circle drawn with this taking the form of this coordinate right here taking the form of sigma x, comma tau xy, and then this one's sigma y, tau xy. And now that's that for that portion, for that question. And we have to find the principal and the normal and the shear stresses on element E. So we found the principal stresses when we did it for the Moore circle for element E. And so let me just rewrite it. E. So principal stress 1 is equal to sigma stress, principal stress A, 3, 1, 5, sigma 2 is equal to sigma B, which is negative 11, 5, 1, 6. So for element E, we now have to find the inclined square orientation. So in order to do that, we have to have our principal stresses, which we found in the last question, as well as our angle of inclination, which we'll find here. So this is the formula for finding the angle of inclination for the first, the angle with the axis with the first stress. And so it's 2 times the shear and the xz plane over the stress in the x minus the stress in the z. And so we find that the angle of inclination is 0.707, and to find the second one, it is 2 theta of the first point plus pi, and that comes out to 2.28. And so we do the same thing for element F. We just change the stresses. So for element F, we did the same thing as what we did for last question, element E, which was draw the inclined square plane. And in order to do that, we need our stresses, and then the angle of inclination with respect to the axes. And so you have your stress values here, and then the angle is calculated again with the same equation. This time around it's 0.75 radians, and for the second point it's 2.32 rads. And yeah, that concludes the homework assignment. Thank you.